Okay, so I wanted to thank the organizers for the invitation. It's been a wonderful conference being here. And I also want to thank Anna. She gave a great talk, and so probably I can skim over and go perhaps a little faster here in the beginning. And so this is taken from a paper with Alvaro Islas on the emergence of solid time like rogue waves that we did. Okay, so as Anna had discussed, in deep water, rogue waves may appear in a regular wave field due to the modulation instability of the background state and nonlinear focusing in a localized region of the sea. The nonlinear Schrodinger is the simplest model, one of the simplest models for capturing the modulational instability and self-focusing. And as such, then these special solutions have come to be used as prototypes for rogue waves because they exhibit all of the qualitative features. You saw very nice plots in the previous talk, and they are localized, they're transient and steep. And in the simplest solutions, the NLS used to model rogue waves are the heteroclinic orbits of unstable Stokes wave. That's also known as the Archimedes breathers. And so just briefly, it was discussed that the Stokes wave is unstable to long wavelength perturbations. And so if you set, I guess I don't have the ability to do that. If you satisfy this condition, then it has an unstable modes. And significantly, each of these unstable modes has a heteroclinic orbit that can be derived by a Beckman gauge transformation, and that's characterized by this wave number mu sub j. And so the figures in the figures, you have the unstable, the background state, the Stokes wave has two unstable modes, and what you have here are two distinct single mode SPVs. And so in the first, you have the SPB U1 that's corresponded to the wave number mu1, and then the second one you have a distinct single mode SPB U2 that has the wave number mu2. And so part of this is to just get used to the notation also. And so these superscripts are being used to indicate the mode that's characterizing the SPB. And okay, so you can iterate the Beckman gauge transformation to create multi-mode SPBs, and this is if the underlying Stokes wave has two or more unstable modes. And so the general form of the two-mode SPB is given here. And each time you iterate the transformation, you introduce a new parameter. And so these parameters, rho and tau here, are determining the times at which the first and second modes become excited. And so in the figures, these are two members of the family of two-mode SPBs. And in the first figure, the parameters rho and tau have been chosen so that the modes are well separated and in time. And in the second figure, the two modes, the rho and tau, have been chosen so that the modes are coalesced and they are excited simultaneously. And so you have this amplification, as Anna mentioned, that goes beyond what you would have with the Benjamin Fair instability. And so generally speaking, the Stokes wave SPBs are typically linearly unstable as their squared eigenfunctions grow exponentially in time. And so before we get to the goal of the talk, I just wanted to say that as appealing as the nonlinear Schrodinger equation is, more realistic exploration of these deep water dynamics can be achieved with a nonlinear damped higher order NLS equation. So this is different from the viscous equation that we were looking at just a few moments ago. We do not have the linear damping in viscous terms. I guess there might have been there at one point in the equation that it got taken out. So that's why you got two pluses. But you know, so when beta is equal to 0 here, you have a Hamiltonian version of the Disti equation, and you've got your higher order dispersion and nonlinearity, and of course the Hilbert transform term, which is reflecting the presence of the induced mean flow. And so with beta non-zero, you are then modeling damping of the induced mean flow. And this allows for permanent frequency downshift. which is another important phenomena associated with the modulational instability. And so the nonlinear damping is non-uniform. And so in this figure, you can see the blue curve is the amplitude of U at a given time slice T star. And the dashed red line is the amplitude of the damping term. And so you see that the nonlinear damping is really only effective near the crest of the envelope. And so stronger waves are going to feel significantly, or steeper waves are going to feel a significantly stronger damping. And so our goal is to examine the stabilization of the SPBs and to examine related rogue wave activity in the framework of this nonlinear damped higher order NLS equation. And so the initial data that's used is generated by using exact SPB data at a time T naught. And so we vary T naught to allow initialization at different stages of the development of the modulational instability. And we also vary the number of unstable modes in the background. And so for small epsilon and beta, you can view the equation as near integrable. And so we are using the flow case spectral theory of the NLS to characterize the perturbed dynamics in terms of the relevant nearby solutions of the NLS equation. And so what we want to address are what are the distinguishing features of the damped flow as determined by the flow case spectrum, specifically which integrable instabilities are excited by the damped flow and which NLS solutions are relevant to modeling the perturbed flow. And how does all of this depend upon T naught, the stage of the modulational instability? Okay. So we'll briefly recall, we've had a lot of talks today, and there was also a very nice talk by Zhishuan, that was talking about spectral theory. So we can just go through this very briefly here. We recall that general periodic solutions of the NLS can be represented in terms of a set of nonlinear modes whose stability is determined by the flow case spectrum of the spatial part of the Zakharov-Shabbat system. And so to determine the flow case spectrum, we let psi be a fundamental solution matrix of the system. And so then the principal object that we're interested in is the flow K discriminant. And it's the trace of the monodromy matrix. And so then in terms of delta, the discriminant, your spectrum is given by all complex lambdas so that delta is real and bounded between plus and minus 2. And so since this is a non-self-adjoint operator, the bands, your spectrum is in a complex plane. And so the spectrum consists of bands of continuous spectrum in the complex plane and these discrete set of periodic anti-periodic spectrum where delta is plus or minus 2. Okay, so to illustrate the main features of the spectrum that we would be using, we'll just discuss it in the context of the Stokes wave. And so the endpoints of the bands of spectrum are given by simple points of the discrete spectrum. And so in this figure, this is the spectrum for the Stokes wave, and you see that we have the entire real axis as spectrum, and there's a band of spectrum along the imaginary axis ending at the simple discrete points IA and minus IA. And there's an infinite number, well, located within these bands of spectrum are these two important spectral elements. The critical points of spectrum where d delta d lambda is equal to 0, and double points of the periodic spectrum, which are also critical points, but they have the additional feature that they have to be elements of the discrete spectrum. And so for the Stokes wave, you see that you have an infinite number of these double points, and the formula is given here. And so you see that they're complex only if your amplitude satisfies the condition, which is exactly the condition for the Benjamin-Fair instability. So you have this link between complex double points and the unstable modes. So there's this distinction between real and complex double points. The real double points correspond to stable inactive modes, and the complex double points typically correspond to linear instabilities. And we didn't say Yeah, we just said you could construct these SPVs by a Beckman transformation. So what you're doing is you're basically building them off of the information gathered from the at the eigenvalues, the unstable, the complex double points lambda 1 and lambda 2. And so the important feature of this transformation is that it's isospectral. So the Stokes wave has this spectrum, and so do the SPVs. Whether you're looking at the one mode or the two mode SPVs, they all have the same initial spectrum. So in all of the experiments, when we start out, this is the initial spectral configuration, which will evolve because we'll be looking at nonlinear damped higher order NLS. Okay, so basically what we find in these experiments and in other experiments is that there are instabilities in the system that are not captured. And here I'm talking about, you know, just NLS. There are instabilities that are not captured by complex double points. And so, so you need to have a broader, or we need, you know, to have a broader flow K spectral, you know, flow K spectral characterization of instabilities for a general solution, periodic solution. And so as an example, if you consider this even standing wave state, which has a cross, it's called a cross state colloquially because it's got this, you know, the appearance of its spectrum, it has this cross, then you notice that there's this intersection of the complex bands of spectrum in the upper half plane. And so you have a critical point. Critical points can arise at the transverse intersection of these bands of spectrum. And going forward, we're just going to talk about critical points as the ones that arise when you are not an element of discrete spectrum. So even though double points technically are critical points, you know, we're calling them separate, just double points. And the critical points we'll be referring to as when delta is not an element, you know, delta of lambda j is not plus or minus 2. And also, I'll only be showing spectra in the upper half plane because of the symmetry with respect to complex conjugation going forward. So if you have an even perturbation of the initial data for this cross state, then basically what it will do is produce a cross state that has a slightly, you know, it has a delta difference in the bandwidth, and the evolution of U naught and U delta will stay close. So you don't have, so you'll have no growth in the difference between these two solutions. But if you have an asymmetric perturbation of the initial data for the cross state, then your band of spectrum breaks here at the critical point, and you have these two disjoint bands, and it can perturb in two different ways. So you can have either a left or a right traveling breather. And so in this case, if you're monitoring the difference or the growth of the difference between U naught and U delta, you'll see that they are diverging. So the experiments that I'll show you later also suggest that complex critical points are related to some type of weak instability, the exact nature of which is under study. Okay, so we're interested in the fate of the complex double points where the SPBs were constructed under perturbation, under the so this is the perturbation under the perturbation to the equation, under the nonlinear damped flow, you will see that these SPBs break up. So, you know, basically what we want to know what happens to the complex double points that we're characterizing these SPBs. We want to see what happens to them under perturbation. And so what we do is we start out by linearizing the initial conditions for the one mode and two mode SPBs. And this is the form of your basic one mode and two mode SPB at t equals 0. And then for small time, we do a first order approximation to the nonlinear damped higher order and less SPB data that it's of this form. But now all of these coefficients here, the A tilde, epsilon tilde, RJ, the thetas, they're all functions of H, epsilon, and beta, where the epsilon and beta are the parameters for the nonlinear damped equation. And so So for simplicity, we're suppressing the explicit dependence on these parameters. And our data is of the form A plus epsilon times F sub I plus Q F sub J. And the Q can be 0 or 1, depending on whether a 1 or 2 mode SPB, whether you want to look at a 1 or 2 mode SPB. And the F sub I's are of this form. Okay, so for data of this form, substituting the perturbation expansions for the eigenvalues and the eigenfunctions into your Zakharov-Shabbat operator, you find that at order epsilon, the only double points lambda sub n that have a order epsilon correction are the ones that correspond to the SPB. So for n equals ij. So all of the other complex or real double points, they don't have an order epsilon correction. And if you are specifically looking at a one mode SPB, it's fairly straightforward to carry this to a higher order. And at order epsilon to the nth, you find that only lambda sub nj will split. So a lambda sub L, where L is not equal to nj, if you don't have an n where you can get this equivalence, then it will never split, which means it will remain there. And so for the two mode SPB, both complex double points will split at order epsilon, and the splitting is asymmetric where you obtain these two disjoint bands. Okay. So now that we are armed with this information, we can go back to the original question that we posed at the beginning, that we want to analyze the nonlinear damped flow with the flow case spectrum. And so just notationally, when we say the n unstable mode regime, we're referring to solutions that have been initialized near a Stokes wave within unstable modes. The initial data is generated by sampling exact SPB data at T naught. The notation here is that whenever you've got an epsilon beta in the denominator, these are solutions to the nonlinear damped higher order NLS. And the superscripts are indicating to you whether you're looking at a single or a two mode SPB, and the IJ are indicating which specific modes you're looking at. And so we're varying also the T naught. So we're initializing at different stages of the development of the modulation stability. Okay. So, so the flow case spectral decomposition is computed at each output time. We are monitoring for the presence of complex critical and double points, and we're also monitoring the lengths of the bands of spectrum in the upper half plane. We didn't initially start out to do that. It's just that in the experiments, we were surprised that, we started seeing that we were obtaining these extremely tiny bands of spectrum. And so the length of the band of spectrum is denoted by gamma, and we set this criteria that when these tiny bands emerge, we view the corresponding modes of the in-phase solution as qualitatively having a soliton-like structure if one or two of the band lengths satisfy gamma less than 0.025. And so, as a motivation, if you consider this example of this is called a gap state. It's a different three-phase solution. And if you take the parameters, if you take the elliptic modular parameters K and kappa, and if you let kappa go to 1 and K go to 0, then basically what's going to happen is this gap is going to close down to a double point and you're going to obtain an SPB. Whereas if you have kappa going to 0 and K going to 1, then the band will shrink to a discrete point at IA and minus IA, and that middle band will collapse to the real axis. So we consider that when we're getting these very tiny bands, that we're getting close to like a soliton-like state. Okay, so to determine rogue wave events, we're examining the strength function S of t. And this is the maximum of the amplitude of U over the significant wave amplitude, which is defined as the average amplitude of the highest 1/3 of the waves. And a rogue wave occurs at time t star if the strength is greater than 2.2. And so to monitor the saturation of instabilities, we examined the growth of small perturbations in the SPB initial data as measured by the evolution of the H1 norm of this difference between U delta and U naught or U. Okay, so I guess how much time do I have? Because I could skip this example.
You have like 20 minutes, including questions.
I have like 20 minutes. Okay, so I won't skip this one then. Okay. All right. So this was set sort of as a warm-up example. It's not as exciting as the subsequent examples. So here, initially the Stokes wave has one unstable mode. And we're looking at the single mode SPB in the one unstable mode regime. And so, as we said, it's going to have the same spectra as the plane wave. And so what you have is this one double point, which is being indicated to you by the large X and the figure. So this is initially what it is. And as time evolves, you know, here we are at t equals 3, and you see that you have this traveling wave configuration in the spectrum. And so the spectrum has split asymmetrically at order epsilon, which is consistent with the short time perturbation analysis of the spectrum. And so you're seeing that U1 is exhibiting this very regular behavior and is evolving as a damped right traveling breather. And there are no world waves in this evolution, so I have no strength plot for this example. And you see that the spectrum persists in this right traveling breather state for the duration of the experiment. The bands just get wider as they move down towards the real axis. But there are no complex critical points. There are no double points, complex double points that occur in the spectral evolution of this SPB in the one unstable mode regime. You don't see any significant growth in the difference. And this is consistent with the prediction of stability from the evolution of the spectrum. And so this single mode SPB in the one unstable mode regime can be characterized as a continuous deformation of a traveling three-phase solution. The amplitude of the oscillations are decreasing and the frequency is increasing until you have these small fast oscillations about the damped Stokes wave. Okay, so now it starts to get a little more interesting. You have now U1, but initially the Stokes wave, the amplitude was such that you had two unstable modes initially, and that can be seen here by the large X and the large box, which are indicating the two double points. And so we're in this particular example, we're initializing at the early stages of the modulation instability. And so you see that damping has split the double points. The first one, this is U1. And so that SPB was built with U1 data. I'm sorry, with lambda 1, at lambda 1. And so lambda 1 is split. I hope I haven't been saying U1 all the time instead of lambda 1. So lambda 1 has split at order epsilon, and lambda 2 is split at order epsilon squared, and they're splitting asymmetrically consistent with the analysis. But what you see then is that unlike the previous example, you have these two short bands that appear, and they decrease, they start to decrease in amplitude and detach and move away from the imaginary axis. And so at about t equals 5, in the first quadrant, this band is less than 0.25, and it's reflecting the emergence of a waveform that's close to a one soliton-like structure. And so you see that in the strength, this is the strength plot now, and 2.2 is the criteria for a rogue wave. And so you see that you're getting a rogue wave at around 5. So if you look further in time, you will find that complex critical points occur intermittently until about t equals 14.7. And there's an example here at 14.2, I guess, was the one where you can see you have a critical point at the intersection of these two bands of spectrum. And so they are appearing in the evolution. And you do have these small bands also. They will enlarge a little bit and then they will come back to, they'll shrink again. And so at T about 15.2, you have another one soliton-like state. And over here, this is a plot that's monitoring the evolution of the band length. And so at this second rogue wave event, I guess I should have mentioned that the red bullets are indicating the times of the rogue waves that we observed in the strength plot. And so for the second rogue wave that appears, it's actually, if you go back, you look at it, you'll see that it's actually a stronger, the strength is larger here on the second rogue wave. And in this case, you see that the band length has gotten even smaller. So it's sort of like the smaller the band length gets, then the larger the amplitude of the rogue wave. And so subsequently the band lengths increase. And here I've only shown the band length corresponding to the spectra in the right quadrant. The other band length never satisfies the criteria. So you only have like a one soliton-like structure in this case. And so, so basically, what we are observing is that every time a rogue wave is observed in the strength plot of U1, the spectrum is in this soliton-like configuration. And so if we look at the D of T, which is the evolution of the difference between U delta and U naught, that H1 difference of U delta and U naught, we see that the instability is saturating, the growth is saturating around 15.2 in agreement with the stabilization time determined by the last critical point. Again, you never get double points. If they don't persist as double points for some reason, you're never going to get double points once the evolution starts. So, okay. So, so the first case was, right. So that example, when we were looking at it initially, it was very exciting because of this issue of getting these tiny bands of spectrum. This example, bothered me for a long time. It's a very nice example. So this is your second single mode SPB, so it's U2, and you're in the two unstable mode regime. And so you see that it's exhibiting very regular behavior in contrast to the irregular behavior of U1 in the two unstable mode regime. It actually mimics more U1 in the one unstable mode regime. And so I'm not showing the spectrum initially anymore. The spectrum for all of these cases initially is the two double points. And so, you see that at a later time, your bands of spectrum, have opened up. Your complex double point that corresponded to lambda 2 opened up, and you then had these two bands of spectrum form. And the perturbation analysis tells you that the complex double point lambda 2 will be opened at order epsilon, lambda 4 at epsilon squared, but lambda 1 won't be split at all. And you actually see that in the experiments. This X here, I mean, I have to get closer to get it, so I guess it's hard for you to see. But this larger X here on the band of spectrum is the complex double point lambda 1. And so basically all it does is just translate around on the curve of spectrum. It doesn't split or do anything. So you're keeping that double point throughout the evolution, in the experiment. And so a distinctive feature for this case is that you also end up having a third mode, lambda 3, move from the real axis into the upper half complex plane, and that one also doesn't split because it's not a multiple. And so the strength plot here is, you know, decaying as you would expect because, you know, there's no real wave activity here. And so the reason this example bothered me and, you know, I did it over and over is because if you look at the difference, so the idea here is that this single mode SPBU2 that it stabilizes very slowly, and it's not until you actually eliminate all of the complex double points, the bands have eventually, you know, completely moved down towards the real axis, and those double points have moved to the real axis, and you know, they're gone, that you don't have any complex double points. The solution doesn't stabilize until about T equals 188. The thing that is very strange is that it does almost nothing for a long time. If you had linear damping, and I ran experiments with linear damping, if you had linear damping on this problem, you would see the difference and the two solutions take off right away. You'd immediately have growth, you know, significant growth in the difference of the solutions. And so then you say to yourself, why is it taking so, you know, maybe something's going wrong. Why is it taking so long for the solution? You know, it's the difference in the error here between them is very small. Why is it taking so long for it to start growing? And I think the reason is because you actually have downshifting in this problem. And I mean, it's a different issue, but I think it's related to that. And so if you look at the Fourier decomposition of the data, it shows that the downshift in the spectral peak, and the spectral peak is the index of the Fourier mode of maximal amplitude. The downshifting is beginning to resolve itself roughly around 100. And so what it seems to be is that downshifting is impeding the growth of these other instabilities. And so it's not until the downshifting is complete that, you know, or almost complete, that you really start to see the growth of the instabilities that are associated with the other modes. And so even if you, so this is the Fourier modes for this experiment. But then if you actually, you know, seed that first mode, so you're taking U2 and you're adding on a small perturbation corresponding to you know, mu1, then it shows that even in that case, downshifting, you know, it impedes the growth. And so the first mode is the blue, I said red, but it's the U1 is going to be the blue dashed line here. And so you see it doesn't start to grow until later. So it's, again, I think it's a very interesting phenomenon, that downshifting, which is something that's very common, you know, in wave phenomena, that it has some sort of inhibition of these instabilities. So then that brings into question, you know, the whole issue of what's the time frame for the instabilities, et cetera, and the magnitude that they actually will achieve in growing, et cetera, if downshifting is impeding that. Okay, so that was U2. And so then finally, the last example is where we look at the two mode SPB U12. So this is the two mode SPB, and so this is the evolution of U12, and you see that damping splits both lambda 1. This little two X's here came from the splitting of the first double point, and then we have the splitting of the second double point. So it splits both lambda 1 and lambda 2 asymmetrically at order epsilon. And you then see that very quickly these two tiny bands pinch off from the imaginary axis and enter this two soliton-like state. And so it stays in a two soliton-like state for a fairly extended period of time, from about 3.5 to 18. And then the spectral bands begin to enlarge, like you see here in this last plot, the spectral bands begin to enlarge. And so you're just sort of evolving like a generic, you know, in-phase solution. And so by saying that this is the pattern and it goes from one soliton-like to 2 to 1, is to just emphasize that it's not oscillating back and forth. It's not going from like a 1 soliton to a 2 soliton, back and forth, back and forth. It will go to achieve its 2 solitons like state, and then it will, you know, sort of dissipate from that. Okay, and so, so the roadway, again, the road wave events are determined from the strength plot and they're given by the red bullets on the band length plot here. That's, monitoring the length of gamma one, which is the blue, and gamma two, which is given by the red. And here's the threshold, the 0.025. And so we see that the road waves are occurring when the spectrum is either in a 1 or 2 soliton-like configuration. And there are no complex critical points or double points in the evolution, and there's also no significant growth in D of t. And so the nearby trajectories remain close for t greater than 0. And so if you let lambda 1 and lambda 2 be the midpoints of those, if you were to look here at this case, where you've got the two tiny bands, if you let lambda 1 and lambda 2 be the midpoints of these bands of spectrum, then, and you compare the two soliton analytical solution with, that you obtain using that lambda 1 and lambda 2 with the numerical solution, you see that there's structurally good agreement near the peak. Okay, so, and so I guess the last topic was just to discuss the dependence of rogue wave activity on T naught, which is, whether you're starting at the beginning of the or when the modulational instability is saturating. In this plot, the blue curve is indicating the time that a two soliton-like state first appears. The red dashed line is indicating the last time a two soliton-like spectrum is observed. The yellow is the last time a one soliton-like state spectrum is observed, and the purple is the last time you have a rogue wave. And so, basically like I said before, this is the pattern. There's no oscillating back and forth. It just goes from this to a 1, then to a generic in-phase solution. And the red dots are indicating that the red dots at each of the sampled T naught are providing a vertical timeline for the rogue waves. And so what you see is that for the solutions that are initialized in the early to middle stages of the development of the modulational instability, the rogue waves are occurring when the spectrum is in a 1 or 2 soliton-like state. But that's not the case when you initialize as the modulational instability is saturating. And so in that case you will have a rogue wave very early on, but you will have a rogue wave significantly after the spectra has left a 1 or 2 soliton-like state. And so in this example, it's initialized right at its peak. And so, yeah, the highest wave occurs here at t equals 0. It's being initialized right at the peak. And so later around 47, there's the last rogue wave, and this is the corresponding spectra. So there's no, there's some other mechanism. If you initialize when your modulational instability is saturating or close to it, there's some other mechanism for rogue wave development. And so I think that's it. This is basically just a repeat. I don't know, I've never liked saying conclusions in a talk because it just feels like you're being redundant. But so we're saying that for U1 and the 2-mode SPB U12 and the 2 unstable mode regimes, and at the time this was very exciting for me because I didn't expect this at all. I mean, we weren't, looking for this, and it just popped out. So these tiny bands of complex spectrum pinch off in the Foucault decomposition of the nonlinear damped data, reflecting the breakup of the SPB into a waveform close to either a 1 or 2 soliton-like structure. And for a solution initialized in the early to middle stages of the development of the modulational instability, all rogue waves occur when the spectrum is in a 1 or 2 soliton-like configuration. But if you initialize as the modulation instability is saturating, the rogue waves may occur due to some other mechanism, and you're not in a soliton-like state. And so for you too, the big, issue there is this growth of instabilities being delayed, possibly by the frequency downshifting mechanism. It's not, until more experiments and analysis is done, but that really seems to be, the likely cause for the delay and the development of those instabilities. And so, and also this issue of complex critical points being significant in addition to complex double points, that they're significant in identifying instabilities. Okay, so that's it.
I think we have time for one big question.
Okay. Oh,
You compute Lux spectrum dynamically and show it only in very few time instances. Is there an indication that it converges to some universal pattern as time goes to infinity?
I only showed it at a few instances. So you're asking in the long time?
Yes, is there some
In the long
kind of
time,
pattern?
in the long time, because of damping it, I mean, it's all going, all of the bands, I mean, it's all going to die down to relax.
That's at infinity.
Yeah.
That's some
Well,
large.
the large time, not at infinity. It gets fairly close, to, dying down to the relaxes, but in terms of, the pattern that we detected was this issue of having these solid unlike roadways, and they appeared, in the beginning, in the initial stages of the evolution, and then after that, it's just, just sort of a generic, in-phase solution, but I always was. I was a little surprised by it, like I said, we weren't looking for it, I always was extolling the virtues of SPPs, and so. Surprised that, okay, yeah, we've got some here. But I know you guys are for it.
Sometimes there are only two bands in upper half plane, but sometimes more bands pop up.
Oh, you mean small bands?
Yes.
Oh, yes, you have the small bands, yes, but they are small.
Mhm.
Oh, I see what you're saying, you were asking about the bands, the higher modes.
Pictured like.
Right, you're asking about the higher modes, yes, those higher modes did not become significant.
I think we'll have to postpone any further question to the tea break, but in the meantime, let's thank Constance